Let's go over what we call displacement versus time graphs. We've seen that from the velocity definition, we could take a big interval and go from the instantaneous velocity to the average velocity or vice versa, delta x, delta t. And if we move the delta t on the other side, we have the average times delta t is equal to delta x. And we've seen that this could be associated with the y, this could be associated with the x, and therefore the magnitude of this concept could be associated with the slope described by a particular line. So if we have x versus t diagram, and we see this. Let's see what kind of motion this describes. Well, we start from this particular time, t is equal to 0, t is equal to 1, t is equal to 2. From t is equal to 0 to t is equal to 1, we can see that our displacement hasn't changed. It's still equal to, let's say, 2 meters. Therefore, if we haven't moved, or if we haven't displaced ourselves, or if we haven't changed our position, our delta x is 0, and therefore the velocity is 0. We could have deduced this from the line equation. If the slope of the line between point A and point B is 0, then we know that the velocity is 0. So whenever you see an horizontal line in the x versus t diagram, you know that the displacement is 0, therefore you don't change your position and your velocity is 0. If, for instance, you see something like this, you know that you have started at this particular position. Let's say 1 meter. And then you have moved to another position. Let's say this one, x2, which let's imagine is 2 meters. Then you have moved to a third position, x3. Let's assume it's 3 meters. You went from position x1 to position x2 in a particular amount of time, and you went from position x2 to position x3, say, in another interval of time. So we know that we have a positive slope. We know that the slope of x versus t diagram represents the velocity. Therefore, from position 1 to position 2, we have a particular speed, which I will call v1. Similarly, from position 2 to position 3, I did it in a certain amount of time, and I happened to calculate the slope and realize that the slope of this segment is exactly the same as the slope as this segment. Therefore, the speed during this part of my travel and this is exactly the same. So the slope is the same between those 2 points, or at each point between this point and this point, the slope is the same. Therefore, I know that my speed is constant over this whole interval. So whenever you have a straight line in an x versus t graph, you always can deduce that the velocity is constant. If the slope is going up, in this particular case, you know that you went from one position to another in the positive direction. Therefore, you increase your displacement, which is positive. Therefore, your velocity is also positive. If, on the contrary, you saw something like this, then you know that you're going from one position 1 to a position of -1 later on. Therefore, you're going in the opposite direction, and the velocity is negative. But every time, and regardless of the magnitude of the slope, every time you see a line describing your motion, you know that the velocity is constant. And it is very different from, say, this scenario where you might see this. Obviously, between this point and this point, the average velocity has a particular slope, which say is 0.5. Then from this point to this point, or this position here and this position there, your average velocity has a bigger slope. Therefore, obviously, you change your velocity and you increased it. Let's keep going from this point to this point again. The slope is even bigger, therefore the velocity went from a small value, or the speed, to a bigger value, to an even bigger value, and even bigger value. So this type of graph tells you that the velocity increases as a function of time. If you see this, then you start with a pretty high velocity, then at this point a little bit lower, then at this point lower, this point lower, this point lower. So what's the difference between those two? Both cases describe a motion going in a positive direction because all the slopes are positive. Case 1, you're going faster and faster in a positive direction. Case 2, you're going slower and slower in a positive direction. What about this? The slope at this point is negative with a big value. An instant later, the magnitude is less, but it's still negative. Less, still negative. Less, but still negative. If all the velocity magnitude or all the slopes are negative, you know you're going towards the left, so in the negative direction. Since the magnitude decreases, you know that you're slowing down, going in the negative direction. If now you're seeing the last case, you start with a negative slope, which is a small value, then you start to increase its value, you start to increase its magnitude again, then its magnitude again. So in this case, the magnitude increases, that means you're going faster and faster and faster. The sign of all the slopes are negative, therefore you're doing this in the opposite direction. So those could be 4 cases that you might see. Now in this course, we will always assume that when you're not going to see a straight line, which means that the velocity is not constant. You're always going to be dealing with a function that is proportional to x2, and we'll see why later on. So whenever you see a function which is not a straight line, you know that the velocity changes. So the velocity is not constant. You can always assume in this particular class that the functional form of that function is proportional to x to the 2. Now let's practice and play a little more with those x versus t diagram. Let's imagine we're given something like this. Straight line horizontal, another straight line. Let's consider point A, point B, point C, and point D. Let's try to describe the motion between each point. From A to B, I'm dealing with x versus t diagram. Therefore, I know that the slope refers to the speed. So I know that the magnitude of the slope refers to the speed, and I know that the sign of the slope refers to the direction. So from A to B, I seem to be increasing my position to higher values. Therefore, I know that I'm going in a positive direction, which is confirmed by the fact that my slope is positive. So I'm going in a positive direction between A and B. I can also notice that the function between A and B is a straight line, which tells me that not only I'm going in a positive direction, but I'm going between A and B with a constant speed. Now let's look at B and C. From B to C, it appears that I had a particular position at B, and that at all time until C, I'm still in the same position, which tells me that my displacement is zero. I haven't changed position. If my displacement is zero, I know right away, regardless of how long it took for me to go to B from B to C, that my velocity is zero, and therefore my speed is zero. Which means that between B and C, I wasn't moving at all. I can get confirmation from mathematics. I know that this is a straight line. Therefore, whatever speed I have is the same between B and C. And as I'm calculating the slope between B and C, I realize that the slope is zero. Therefore, my speed or my velocity magnitude is also zero. Okay, so far so good. Now let's look at the case between C and D. Between C and D, I seem to change my position to lower and lower value from C to B. Therefore, I'm starting with a position of 3, then sometime later my position is 2, then sometime later, and now it's only 1. So obviously I'm going towards the negative direction. So I'm moving backwards. And I notice that the slope between C and D is unique because this function is a line. Therefore, I can deduce that this is a constant speed. So I'm changing position with a constant speed between C and D in the negative direction, which can be confirmed by using the mathematics again. I know that between C and D I have a straight line, therefore constant, and the magnitude of my slope is going to give me a negative number, which tells me that I'm going in the negative direction, and the actual number will tell me the magnitude. If I compare the magnitude of this slope with the magnitude of this slope, then I can deduce clearly that I'm going back to my initial position 0 between C and D at lower rate than from A to B. So let's say if this is 3 meters, it appears, and let's say this is 2 seconds, 2 seconds, 3 seconds, 4 seconds. My motion would be from t is equal to 0 to t is equal to, wait a minute, let's use 1, 2, and 3, sorry. The first second, I went and displaced myself 3 meters. Then the second later, I stayed there at position 3. Then the last second, oh, hang on, so I need a 4. So 1, 2, and let's say 4. Sorry. So I went from position 0 to position 3 in 1 second. So I travel in the positive direction. Then between B and C, I just stopped there for 1 second, from here to here. Then from C to D, I went back to my initial position, which was 0. But this time it took me twice as long to go back. Therefore, my velocity vector in this direction was a big vector, while the velocity vector from C to D was half the magnitude of this one. It took me twice as long to go back to my initial position. Let's try another one. A to B, B to C, C to D. From A to B, it appears that I'm changing my position, but the slope, which represents my speed, seems to increase. Therefore, I'm going faster and faster and faster in a positive direction between A and B. From B to C, it appears that I'm staying in the same position because my x doesn't change. Therefore, from B to C, I'm staying still. Again, I can confirm this because my slope is 0. Then from C to D, it appears that I'm going back to my initial position that I had when I was in A, except now I'm going it with a constant velocity because I only have one slope. So I'm going in a negative direction between C and D, and I'm doing it with a constant speed. While B to C, no motion. Once we investigate the concept of acceleration, we will be able to say a little bit more about this region. Again, whenever you're going to see something like this that doesn't look like a line, you're always free to assume that this is proportional to x2. That's it.